Okay, let's resume our exploration of moduli spaces, etc. I'll try to talk about these 4 items. Maybe I'll leave out the last one. I don't know. It's time permitting. So, first completions. So completions, I had said very little, but I want to make it concrete. So again, the theorem was, I don't write it out in full. It's just that MGN sits inside MGN bar, and the difference, MGN bar.
You write a bit bigger.
Bigger. MGN is, among other things,
a bar in the first one?
This is a bar.
And the other one on the left?
No, you mean oh yeah, I should write this. Yeah, it's a notation. The boundary of it's really, you take it as a notation, equals a divisor with normal crossing. Well, so what does it mean? How do you see this? So there are several ways, many ways. Well, no, 2 ways basically: complex and algebraic. So the complex ways is to say that MGN bar minus MGN is made up from Riemann surfaces with nodes. Okay, so you have typically this surface where here you have a node sits into the boundary of M3. I should put bar maybe. And the boundary of M. So when I say this surface, doesn't mean anything. It's purely topological. So what it really means is dm3 contains, actually what has an irreducible component, which is isomorphic to M12 cross M11. Because this is M1, sorry, M21. This is M21, genus 21 mark point, and this is M11. And at the boundary of M3, inside this divisor, there's one of the component is this, M21 cross M11. Okay, because you can vary this and you can vary this. What do I want to say? Yes. So this picture is close to what people draw when they draw bubbles. You know, people like to draw in this program. They like to draw bubbles. So in genus 0, that will be the analog of bubbles. But what? In some sense, well, let's say this is the complex analytic view. But let's take the hyperbolic view. What do these surfaces look like? What has happened here? Let's try to be more specific. What is it that has happened? What you've done is you start from genus 3. Well, maybe genus 3 is a bit ambitious. I can't draw it very well. And you have singled out one curve. Okay. So fact. Now I revert to the hyperbolic view, which is very useful too. So this would be like the conformal view, and you can think of the bubbles that people draw when they speak about configuration spaces in genus 0. But from the hyperbolic viewpoint, what do you do? And it's quite useful. I mean, it's really even necessary. You take a curve. There is a fact. There exists one and only one geodesic in every homotopy class of simple loops on, what should I write, on S, I mean on S equipped with a hyperbolic metric. So on I can say X, which let's say i.e. S equipped with, so everything is modeled on S. I equip F with either a complex structure or a hyperbolic metric, same thing. So S equipped with a given hyperbolic metric. Okay. So on a surface, there's one and only one geodesic per homotopy class. Okay, so I take this, so I can consider this as a geodesic. And then, you know what I do, I squeeze it, which has a well-defined meaning. It means that, you remember this Fenchel-Nielsen coordinate, it really means that in the Fenchel-Nielsen coordinate, I make this smaller and smaller. It was one of the numbers in the coordinate. So what happens when I make it smaller and smaller? This is what differs from that thing. What happens is that there is a long annulus, so it looks much more like this. This is how it should look like. Because when you squeeze a geodesic, it's also a fact, a proposition, that there's an annulus ring of large conformal modulus which appears. And the thing, and then until you get, so, I mean, you never get it, it's asymptotic, but in the completion you get a cusp. Okay? So the fact, another fact, a proposition which is really beautiful and useful, and actually it's one of the key facts for the two-level principle, but I'm not sure I'll get there. It's called the color lemma, and it's a lemma. It's an interesting phenomena in hyperbolic geometry, which it says there exists I'll show it to you. There exists a constant. I mean, not only there exists a constant, but I think it's log of 1 plus square root over 2. So, I mean, it's completely explicit. Let's call it C. Let's say C is somewhere between 1/2 and 1. I'm not sure. I mean, it is just a number, which is completely explicit, such that on any, I'm always tempted to write on any Riemann surface. You see what I mean? I mean, on any Riemann surface. Again, when you speak about geodesics on a Riemann surface, it's you mean that you take the thing of the metric of curvature minus 1. On any Riemann surface, two closed geodesics of length at most C do not intersect or disjoint. This is a very basic and very interesting phenomenon in hyperbolic geometry for surfaces. And well, you can extend it, but it's a bit more complicated. So you can see it here in a way, because well, here when you have a small geodesic, you have an annulus of large modulus which appears. So if you want to cross that geodesic and be a geodesic, you have to do all this. And then, of course, you will be long. So this is really an interesting point, and it allows you to describe the the boundary of moduli space in a very, not explicit, but in a very pictorial way. Maybe I'll have a chance to say it better. So you have this, and what do I want to say? Yeah, and so okay, so this is more like this, and so in genus 0, let's go back to genus 0. So what happens in genus 0? In genus 0, well, you have well, maybe it's a bit premature if I want to say something. No, genus 0 is the same thing for the time being, so sorry. It's not very specific. I mean, it's much easier, but it's not very specific yet. What I want to say is what? Oh, yeah. Maximal degeneracy. So maximal degeneracy, what is it? It corresponds, there's a bijection with maximal multicurve. So what does it mean? I mean, how can you degenerate your surface? By collapsing geodesics. How can you maximally degenerate your surface? By collapsing as many geodesics as possible. All these geodesics have to come from a multicurve. The thing we had this morning. So let's do it again. So if you want to collapse the maximal, I take the same one as this morning. Let's take the same one. So this, which is not necessarily very standard, but in some sense a bit standard. Okay, take this one.
Not the same.
Maybe it's not the same. No, it's not the same because there's one missing, no?
So you have the ones that you don't.
And maybe I had these, yeah. Well, it doesn't, I mean, doesn't matter. Okay. Any multicurve. So first, from what I told you here, from the color lemma, this says what? You're in M3, and you're sort of drifting toward the boundary of M3. So the strata of, so M3 bar, so maybe I can say this, MGN bar has a stratified structure. So where the strata in codimension whatever, I mean codimension, the name, codimension C, oh C, a name A, D, M, correspond to multicurve, to M multicurves. So an M multicurve is a curve with M of these. Sorry, a multicurve is not necessarily maximal. This is a multicurve. A multicurve, an M multicurve, definition is same as this morning, a set of M non-intersecting simple loops up to isotopy. Everything is always up to isotopy. Okay, so you take a multicurve, and if you degenerate along the multicurve, you're approaching a stratum in the boundary of codimension M. So if M is empty, if M is 0, if M is empty, you're not doing anything. So the stratum of codimension 0, the generic stratum, is MGM itself. Okay. Then the strata of codimension 1 will occur when you degenerate one along one curve, one loop. So you get one node, and the strata of codimension M also correspond, or Riemann surfaces with M nodes. Okay?
One question. So you're talking about the length of geodesics, right? Are you going to say something about the points? They are
Oh, the
endpoints.
Oh, the endpoints, not necessarily. The endpoints play. I mean, they're treated in exactly the same way.
They what?
They're treated in exactly the same way. For instance, if I'm in M12, you should look at this way. The M32. This is in M32. So the points are always cusps, okay, in this picture, and then you simply add whatever number. So you should have this. This is a multi-curve. Well, this would be a maximal multi-curve on a surface on S32. So from this viewpoint, it makes no difference. So you don't treat the points as points. Huh? You treat them in a topological way like this. They're curves. But that was a bit ambitious. Well, in fact, it's okay. So the strata in codimension n correspond to blah, blah, blah. So the points have maximal. So the strata in codimension m have codimension m. So the strata which have dimension 0 have codimension, the dimension of the space, are those which correspond to degenerating along a maximal multi-curve, which has exactly the number of curves equal to the dimension of the space. Okay, so nature is well done, and so you degenerate along a maximal multi-curve, and if you degenerate along such a maximal multi-curve, you will what will you get? What will you get? You'll get a graph of a stable graph, I should say, a stable graph of our favorite objects, of copies of P1 minus 3 points. So I shouldn't put it this way because I was doing it in a conformal way, or so write it this way if you want. C minus 0, 1. Okay. I wrote it in an algebraic way, but it's the same. So here you can. I won't do it otherwise. You can do it on your paper. I mean, you have a graph. So this is P1 minus 3 point. This is P1 minus 3 point, and then you just stick it together. So if you really say it's P1 minus 3 point, you just draw a line. That's all it. I come to this now. You draw a line because it's. If you do it in an algebraic way. If you do it in a conformal way, this is it. No, sorry, this is not it. You want to squeeze. I'll not attempt to draw. At least this is too much. Okay, now what I want to say is, in this stratification, so you have points, the points of maximal degeneracy, they're obtained this way. What are they? Why are they special? They're special because, well, they're not special. They're special because the point is, the curve is well defined. These are rigid objects. Okay? What I'm saying is that if you have a graph of these objects, this is a well-defined analytic or algebraic object, and then you can try to deform it. All the other strata have some dimensions. They have some modular parameters. Okay, I'm saying that this is m21 times m11. So here you have a modular parameter, which is usually tau, and here you have a n21 as dimension 4. So you have 4 modular parameters. When you come to maximally degenerate points, you don't have modular parameters at all. They're just rigid objects. There's zero variation. Okay. So from the point of view of, so let's go now to genus 0. So what are the maximally degenerate points in genus 0? In genus 0, you repeat that same thing, except it's a stable tree. I didn't explain stable, but let's forget about stable. It's a tree, okay? So that's what we had last time. If you have this, say this is in M05. So one way you can see it is just by fleshing this. So here you have only mark points. So this is literally, you do this, what is it? It's literally the surface itself. It's S05, just a little before it collapses, so to speak. So this could be longer. I mean, when it collapses, it's long, and so on. So genus 0, you have trees. So these trees, and they essentially look like the surface. So the geodesics are here. So here you have only 2, okay? M05, dimension 2. You have 2 geodesics, which are collapsed, or nearly collapsed. Could be longer, should be longer. And so that's one point of maximal degeneracy in M05, but they're all the same. I mean, they only differ by labeling.
Okay, so it is a point on M05 bar.
It is, yeah. The way I draw it, it's a point on M05, which is close to the boundary,
Yeah.
which is even close to a point of maximal degeneracy.
Can I think of an exponential map? Decimal 1 to.
Yes, you can. I mean, I showed you the Fenchel-Nielsen coordinates. You can certainly degenerate in one direction.
Yes.
Okay, you simply collapse in that way. So what do I want to say? Oh yeah, from the what do I want to say? What can you say? What should you say about? Yeah, maybe I'll show you a few pictures. Add pictures. Let's show you a few pictures. So rather than So for genus 0, so for genus 0 you have this these trees. So you have the number of internal edges is the dimension of the space. So any internal edge corresponds to like these two here. You have 2. So the internal edges give the dimension of the space. You have the multicurve as many elements as the number of internal edges. So you see that in M03 is 1 point. Okay, so there's not much to do. M04 you have only 1 tree, up to renumbering. Okay, n equals 5 you have 2. N equals 6 is the first time where you have 2 different trees. So you have 2 different types, numbering notwithstanding, of points of maximal degeneracy. N equals 7, you have 2, and so on and so forth. And so on and so forth. So just evermore. What do they look like? Well, what?
Just to make things clear for me, when you say graph of pi1 minus 3 points, in the picture here's pi1 minus 3 points are
this
point, and the edges are the
yes. Okay. Okay. Now the graphs which are here are the dual graphs, which look like this, which are easier to draw in the in the algebraic language, which we've seen last time, what's happening is simply that when on the line you have these 3 points, and when you have the fourth, which like comes near, what you do is you blow up, and you get this. So these are the dual trees, the trees which are dual to these, okay? Dual to the last ones. So compared to these, internal edges are lines. Well, I should put them together, but it's a bit difficult. You see here you have this picture. Now, any internal edge now is represented by a line. So you have one line, then 2 lines, then like this. The points are on the line, and the intersections are the intersections. So what is happening? Another. How do you describe? So in M, for any G, any N. Okay, take for any. So let's say proposition for any P in MGN bar, a point of maximal degeneracy. There is a complex neighborhood. I mean the complex topology, which is isomorphic to this. So D equals 3G minus 3 plus N is the dimension of your space. D small d, and D star is the punctured unit disk. Punctured unit disk. Why? Because I mean you have to do it. You do it locally. So what's happening when you do it locally? Locally, what is happening is you have any of these pictures, and you have the 2 Fenchel-Nielsen coordinates, which are the radius, the length of the geodesic and the twist. And the length of the geodesic and the twist give you this. Sorry, I should say there's that thing is a complex neighborhood. No, then it's this. It's the trace on MGN is this. When it's a 0, then you're on the boundary. When it's not 0, it's not on the boundary. So let's say MGN. So let's say a complex neighborhood V. So now if I take consequence V intersected with MGN of R is homotopy equivalent to S1 to the N to the D. Well, homotopy equivalent is a grand world. I mean, no, I'm sorry. Wrong. This is equivalent. No, MGN. Okay, sorry. This is true. So I write C. Okay, this is true. And now when I intersect with the real part, MGN R falls into 2D, 2 to the D, 2 to the D, I hope so, yeah, 2 to the D, simply connected regions. Connected off. So it's not connected. I'm saying very simple thing. I'm simply saying that you have this disk. It's a product. So you have this disk. Here you have the point which is on the boundary. Okay. So if you intersect with the smooth part, you have a punctured disk, which is the same as homotopically as a circle. And now if you intersect with the real part, you have these two things. You have these two parts, 1 and 2. These are the points, these are the tangential base points. These are what we call the tangential base points. It's not complicated because it's really a product on each and every curve, a loop, the same thing happens. Just a product. So I'm just degenerating one loop at a time. Or then when I degenerate all the loops, what I can do is, again, when you degenerate, what you can do is you make it this smaller and smaller. And to completely determine what happens here, you also have a twist. So when you do this, well, this is not. I mean, this is just a description of what happens, and it's not difficult in the sense that it's just a straightforward description. These two to the d simply connected regions are the tangential base points. So now, if you do it, so what does this tell you? It tells you that you have trees. These trivalent trees, which we see so often in the program. This trivalent tree corresponds to points of maximal degeneracy. Okay. But careful, trivalent tree here not embedded, not embedded. Because if I embed them, I'm doing something. These are abstract trivalent trees. Okay. Their dual are the ones which you see there, but forget about the dual. Just these trees. When they're embedded, we've chosen something. So the embedded trivalent trees, correspond to precisely tangential base points. Tangential base points. Why? Because how do you enumerate the embeddings of a tree? By flipping along these edges, along these internal edges. What can I do here? I can do a half twist, okay, along any of the internal edge. Okay, along any internal edge, I did a half twist, and then that will enumerate all the embeddings of the tree in the plane. And these half twists precisely correspond here to going from one connected part to another. This is a half twist. I go from the tangential base point, which in dimension 1 we like to call 0, 1, to, well, here would be 0, infinity. I mean, mine, the opposite. Okay, when I do a twist on moduli space, I return to the same point. When I do a half twist, when I perform a half twist, I'm not. It's not a loop on moduli space. It's a path, which goes precisely from one of these tangential base points to another one. So here it corresponds exactly a half twist to enumerating the embeddings of the tree in the plane. So the embedded trivalent tree corresponds to tangential base point. The trivalent tree corresponds to point of maximal degeneracies, and what? And I'm not talking about this the thing we had. I mean, which bracketing, say, patterns, which. I mean, this V1, which we've seen yesterday again. Things like that, which they correspond. I mean, okay, you start. Well, I don't do it. This is the simplest thing. You to any trivalent tree, and to any embedded trivalent tree, you can let correspond a bracketing pattern, and that's completely combinatorial. You start here and you say that these blah blah blah. Well, we can do it, but we've done it several times. So forget about this. Although, of course, when you do braided categories, you get here. Braided categories, you like this or whatever, but they are exactly the same. What you can do in any genus, all this is true. What you cannot do in any genus is what I did last time, and I'm not going to do again, is opening the nodes in an explicit way. Even in genus 1, it's very, very difficult. I mean, when you let an elliptic curve degenerate, you're not going to write down equations like that. It's complicated. When you're taking a rational curve and let it degenerate, it's very easy. You just write down simple equations, and it's completely explicit and actually quite easy to compute. Okay, but we don't need to. Okay, so we have this. Now, let's go. Yeah. We have to move on to curve complexes, but we know what they are already. Curve complexes. So curve complexes. That we've done already. A simplex. So it's so given S. So the definition is given S equals SDN. Okay. I mean with C of S is the simplicial complex with one simplex, with one K simplex for every K plus 1 multicurve. So if you give yourself, so for a zero simplex, so a vertex actually, a vertex is given by a loop. Okay, by one loop. A vertex is one loop. A face is two. An edge is two loops, etc., etc. So it's C of S is a simplicial complex. You can say of dimension d minus 1. D equals dgn equals 3g minus 3 plus n. So it has dimension d minus 1. We've seen it already. Okay, so but now you can give it the structure of a simplicial complex. But we need another complex, which is the Pence complex. And this is the one we need here. This is extremely useful, but I'm not sure I'll talk much about it. It's completely connected to this, but I want to first get to this. The Pence complex so definition. It is so same thing. Cp of S is a simplicial complex. A simplicial complex of dimension 2. Dimension 2. So vertices are the maximal multicurves. So the so-called Pence decomposition, maximal multicurves. So we know them already. Curves. Edges are of two types. A moves and S moves. I'll show you what they are. So A moves and S moves. So the A moves are, okay, suppose you have two So these edges live on, they live on surfaces of modular dimension 1. So the surfaces of modular dimension 1 are just S04 and S11. By modular dimension, I mean the dimension of the attending moduli space. So if you have two Pence decomposition, what am I supposed to give you? I'm supposed to give you an edge joining two maximal multicurves, which I call P because Pence decomposition. So I'm supposed to tell you when do I put an edge between two maximal multicurves. And the rule is very simple. First, they have to differ by only one. Why do I always choose genus 3, which is a bit of a drag, but okay. I don't want to choose genus 2 because it's a bit too simple. I don't know. So they have to differ only by one element and to be connected by an S move or an A move. An A move lives on a surface of type 0, 4. So let me write it this way. So P is purple. And P prime is, I don't know how to write it, purple plus green, plus yellow. It means, very bad. It means I erase this and I put the yellow one instead. So they differ by only one element. So it's purely local, okay? We're local on S. That's very important. This is the sense of local on S, the sense of local even in the statement I was giving you. So in the end, the rest of the surface you don't care. So what you're doing is you do this, and you replace this by this. So what is it? Oh, sorry. I guess I should do that. So what is it? Well, you know it, I mean, better than I do. So it's a Heidemeister move. But how do you see it on the moduli space? On the moduli space, on M of S, let me write M of S for the moduli space of S. This corresponds to a path between two adjacent, adjacent maybe with quote, points of maximal degeneracy.
Is that an A move or S move?
Sorry? That's A move, A for associativity.
What's the difference?
S I haven't explained yet.
Okay.
A, this is genus 0, okay? In the sense that, I mean, the thing can be any genus you want, but here you have 0, 4, okay? So this is a move which lives in genus 0, and this is one you know already, because this is the A move, and this is also the small a I had when I deformed the associativity, and this is also again the P I had when you're on P1 minus 3 points. Because maybe now you see better, I mean, maybe it's more obvious that when you go from 0 to 1, what are you doing? You're doing exactly this. When you go from 0 to 1, when you're near 0, this, okay, you have 0, 1, infinity. What does this surface look like as a hyperbolic surface? It's a sphere minus 4 points, 2 of which are collapsing. So this is it. So say, for instance, if I number it as 1, 2, 3, 4, this would be 1, 2, 3, 4. This is not an analogy. This is an identity, provided you consider this as, so you pass to the analytic category if you want. You make it hyperbolic, and this is it. This is your object. Now, when you go along P, and you travel along P, and you come here, this is it. 1, 2, 3, 4. Because now 2 and 3 are close, okay? And the geodesic here is here. And this one is collapsing. I mean, actually, this should be much longer again, and this should be much longer. So this is not, again, an analogy. It's just what's happening in the hyperbolic picture. So it's also a Heidemeister move when you put it in a graph or in a combinatorial context. Okay? So this we know already. The S move is in, so I haven't given you what the S move is like. So the S move is the only ingredient which has to do with the genus. Well, not the only, but the only in these contexts. So the S move is the same, well, it's this. It's the only thing you can think of, actually. I say S move because S is for simple, and simple is the term, I mean, it's a bit bland, but that's how Thurston calls it. So it's Thurston's terminology. So it goes from here to here. So that's an A move. So be careful. What do I mean by A and S here? Oh, sorry, S. That's an S move. So I mean, of course, this is not well defined, the yellow curve. It maps to, I want to go to any curve which has intersection, which has 2 points of intersection with the others. There are more complicated ones, which I will not attempt to draw. Yes, I mean, basically, the third one is this. You'll see it on the screen in a second. Okay. There are of course other curves than this one. I mean, don't be sort of fooled by the blackboard. Of course, this one is not well defined. It's just any curve which has 2 points of intersection with the purple curve. Same here. I don't mean that this goes to this necessarily literally. It goes to a curve which has only 1 point of intersection with the purple curve. Any curve which has only 1 point of intersection with the yellow curve. With the purple curve. Okay, that's an S move. Okay? So these are the edges. But I have to define, I have to show you what the faces are. And the faces are on the screen. Well, soon. The faces are on the screen. Oops. Right. So you have 6 types, but the 6 types are, I mean, you'll see they're not difficult. They're not difficult to guess even, almost. So, sorry, it's a bit pale, but so you have a cycle of type 3A, which means a triangle of curves. Okay, what's a face? What's a face? Here it's a triangle. You have 3 pants decomposition, but a pants decomposition in one curve. I mean, these things are completely local. It's only one curve. So you have 3 possible curves. Sorry for the fact that it's pale. So they're called here beta 1, beta 2, beta 3. So I can attempt a drawing. So it's this, and this. Okay, so there's 3 curves, and you put a face whenever you have a triangle like this. Then you have another triangle. Then you have let's stay with genus 0. You have the pentagon. This is the pentagon. This is the usual pentagon. Maybe I should also translate. You have, so why is it a pentagon? You have 5 curves. You have 5 curves which are beta 1, 2, 3, 4, 5. No, 4, 5. A Pant's decomposition is made of 2 curves. Okay? Pant's decomposition, M05 has dimension 2. So Pant's decomposition is made of 2 curves. So one way, maybe one way to describe it, I think I have a transparency which may be, which is exactly the same it's a translation, but sorry. Oh yeah, I'll show you another pentagon which is the same. So you have the usual pentagon, Drinfeld, or I mean MacLane, rather, the one which is used in Drinfeld. And here you have this, I drew it this way. The 2 things are always a Pant's decomposition. Okay? The yellow things which circle the 3 points is equal to the other one. You know, if you circle 1, 2, 3, 4, 1, 2, 3, it's the same as circling 4 and 5. We're on the sphere. Okay? So what you forget about the yellow circles. A Pant's decomposition is, for instance, 1 and 2 and 5 and 4. So this is the pentagon, exactly the same as above. And this is also the same as the one I had, which is here. Yeah, here. When, you know, at the bottom, it's beta 1. You see, it's this chain of Pant's decomposition. It's the same object. And for any of these objects, you put a face, 5, I mean, you put a pentagon. Then come the 2 last types of faces, which are genus 1. There is one triangle in genus 1, which is the same as the triangle in genus 0. Actually, it's the same in a completely well-defined way. It's the same because if you project to genus 1, if you take your elliptic curve, you project to genus 0. If you take your genus 1 curve, you project it down via the Weierstrass point, you find the other triangle. But anyway, you see you have 3 curves, beta 1, beta 2, beta 3. That's a triangle in the sense that 2 of them are always connected by an edge. Then you put that thing. And you have the last cycle, which is in some sense the most, which will give rise to the only new relation. This is the cycle. We call it 6AS. So you have 3A, 3S, 5A, and you have 6AS. So 3A has to do with M04. This is to do with M11. This is to do with M05. And this is the most mysterious. Well, no, it's not mysterious. It's the added one. It's to do with M12. So it's 2 points. You see, it's 2. It's genus 1 with 2 marked points. Okay, so there are several things you can say, but okay. So the theorem, which makes things work, is, so the theorem is, so the theorem, Cp of S, so if, maybe if D of S is bigger than 2. Well, D of S means modular dimension. Okay, S is SDN, and D of S is 3G minus 3 plus N. If D of S is bigger than 2, Cp of S is connected and simply connected. This is the analog, so in genus 0 would be MacLane coherence theorem. But this is much more difficult. MacLane's coherence theorem is, I mean, once you've thought about it, I mean, if MacLane had thought about it, it's not difficult. You have your patterns and you have your hexagon and pentagons, and not difficult. But this is really difficult.
So this is, when you say connected and simply connected, it's related to the homology of this complex.
This is a simplicial complex, so if you can say, if you want, you can say that the geometric realization is connected and simply connected. It's a simplicial complex, so you just realize it as a and then the simplicial complex, the realization is just connected and simply connected. And this is what makes things work. And it's connected, so to speak, it's connected with the two-level principle. But that I will not have time to explain, probably. So now I have another 15 minutes, but there's not much to explain. To tell you how you let something like GT act on all this.
So excuse me, maybe you said, but A stands for associativity.
A stands for associativity. S stands for simple.
Simple.
Yeah, it's not a good terminology. It's Thurston's terminology. Maybe I can tell you the story. I was trying to understand what you could do in higher genus. That was a long time ago. And then I was trying to study Thurston and so on. And then they have a paper which is quite well known, a paper with Hatcher, which is the paper where they prove that the mapping class group is finitely presented. Actually, Dehn proved that the mapping class group is generated by Dehn twists many, many years ago, I mean in the 1920s. And but then for a long, long time, people couldn't prove that the mapping class group is finitely presented. So actually, there was no presentation, and there was not even a proof that it would be finitely presented. So finally, somebody came up with a proof which is purely combinatorial and algebraic. I think somebody called McCool. But then that was a bit overshadowed by what Thurston did. So he applied the strategy which was devised maybe which is known to Weil, say, which is to let the group act on a highly connected simplicial complex and deduce something this way. If you let a group act on a simplicial complex which is at least two connected, then you can devise a presentation of your group. So, for instance, it is difficult, really difficult, to prove that the curve complex, to find the homology of the curve complex. That's part of it's part of a long story. So they proved in the paper by Hatcher Thurston, which is when was it? I don't remember the date. They proved that a certain complex was simply connected and a little more, and etc. And in the appendix, they mentioned that complex, and that they probably what could do the same. Finally understood that we needed that complex, and we sort of outsourced the work, which is we simply wrote to Hatcher saying, could you actually prove this? And he proved it. When I say it's difficult, it's really difficult. Namely, you have to use the full force of what is called Cerf theory. I don't know of any other proof. Maybe there are other proofs now, but also for that's what they use with Thurston. Cerf theory tells you what happens to the bifurcation of Morse functions on a surface, because you can think of these things as like short. I mean, well, you can as you can take a Morse function on a surface, and you can look at its critical points, and then you can look at the global bifurcation of critical points of a Morse function. That's a complicated story, a complicated theory devised by Cerf. Cerf classified these bifurcations. These bifurcations are basically what happens here, and this is how you prove that these complexes are have a certain connectedness. So it's really difficult topology, because even Cerf took a long time to devise that theory, and then you have to use it in a non-trivial way. And I'm not saying I could do it. Now, suppose you have this theorem. We do have this theorem. I can finally try and explain why you can let something like GT act on your mapping class groups. So, so, what should I do? Wait, sorry. Do I need? Yeah. Oh, maybe first I give you. Yeah, first it's very relevant. I need to give you first a presentation of the mapping class group. The presentation I'm giving you is very nice. It's absolutely not finite. It's not a finite presentation. I take as generators all the Dane twists. So you take as generator all the Dane twists, so it's certainly not finite. And the relations are very simple, and that's what one needs. Actually, in the Esquisse d'un Programme, Grothendieck already fulminates against people who are so stupid as to consider finite presentations, which are really not useful. What you need is presentations that are local in some sense. So this says that you see between Dane twists along. So I use the convention of the topologists, who write loops with the Greek letter and the corresponding twist with the corresponding Latin letter. So A, for instance, A is the twist along alpha, and B, etc. So of course, if you have two loops which don't know each other, alpha and beta do not intersect, then the corresponding Dane twist commute. If they intersect at one point, then you have the braid relation, ABA equals BAB, and that's the only thing you have in genus 0. And, you have also this one. You have what is called the lantern relation. The lantern relation tells you that if I have a triangle on a surface of type 0,4, then I have ABC equals the product of the boundary twist. So if you forget about the boundary twist, for instance, if these are cusps, you have ABC equals 1. And the very last one, which is the only one which is genus 1, which is not genus 0, is this one. You have a twist alpha. So let's say you have a twist alpha, like here, alpha. And you have the twist beta, the twist along beta, and you have ABA equals the boundary twist. This is something you almost know in SL2Z. In SL2Z, it's almost in SL2Z. Sigma 1 equals 1, 1, 0, 1. This would be A. B would be sigma 2 equals 1, 1, or minus 1, 0, 1. And then you have sigma 1, sigma 2, sigma 1 squared. Here it would be equal to minus 1. So in PSL2Z, this is 1. Here, the only thing you have is you have a boundary twist. So it's not 1. Did I say something wrong? ABA to the 4. Yeah, ABA to the 4. Because this is sigma squared, but you get minus 1. So if you raise it to the 4, you get 1. Because here you don't have a boundary. So this is a relation which almost lives in SL2Z. Okay, so now, if you know this, the presentation of gamma will allow us to act on it, so to speak. What I said is a bit shallow, because in order to obtain that, there's a lot of work involving precisely the curve complexes, etc., etc. Okay, so this is the result of tons of work which precisely involve these ingredients. But okay, suppose we know this. So what you do, I give you a recipe. So the recipe is as follows. Maybe, well, I don't know if I need this, but what's the recipe like? Yeah. So how to act on, but careful, gamma, G, and hat. Okay? Because it's the same that we had with Drinfeld. If you try to act on gamma Gn, you will find nothing. So plus or minus 1. So you want to act on gamma Gn hat. So you pick, so it's a recipe, so the ingredients, you pick a Pence decomposition, a maximal multicurve, same thing. So you pick a maximal multicurve. I stubbornly work in genus 3. So yeah, I pick a maximal multicurve. Any maximal multicurve, make it different. No. Oh, I shouldn't have made it. Yeah. Pick a maximal multicurve and decree. So first step. So I want to have an f. I have an f equals lambda f. Start so in dt. I'm not saying it will work. I'll have to add one more relation. But mark the fact that the ingredients are the same. So lambda, again, lambda is not so crucial. Lambda is the thing which acts, you know, when I was doing this, around a tangential base point. Around a tangential base point, what you do is, you do this, and you do this. So lambda is the cyclotomic character. It acts when you pass from one tangential base point to another one around the same points of maximal degeneracy. So it's not so important. What is important is f, again, as usual. And f is the same. F is the same ingredient as usual. Do this and decree that for any, how do I call? I mean, what letters do I use? For any what? Yeah, for any alpha in T, f of a equals a to the lambda. So a is the twist along alpha, so a equals tau alpha. A is the twist along alpha. And f of a, so you decree, I mean, you decree that nothing happens, nothing happens, yeah, except for this lambda. So what you've really done is you've picked a point of maximal degeneracy on your moduli space, okay? When I say pick a maximal multi-curve, always forget multi, it's the same as saying equals a point of maximal degeneracy in M of S, which is MGN for some G and some N, okay? Of M, well, in MGN, I put it. Okay? It's the same thing. So, what again, I mean, not again, you have a groupoid where all the tangential base points are, there are finitely many of them, are at the points of maximal degeneracy on MGN bar. Okay? So maybe I should put MGN bar. And you pick one of them. Like, for instance, when we did it with P1 minus 3 point, I picked 0, 1. Okay, but you can pick another one, it makes no difference. It's just an inner automorphism. So now, the recipe is as follows. The recipe is as follows. So I put it here and I'll copy it. So if A and B, now if alpha and beta, well, how do I say? If P and P prime, if P and P prime differ by an S move, which maps alpha to beta. So if they differ by an S move, it means that the two maximal multi-curve, which actually are maximal points of maximal degeneracy, differ by just one curve. One I call alpha. Maybe I should call alpha. Well, sorry, they call alpha and beta. I guess alpha and alpha prime would be more logical. So they differ by just one curve, and they differ by an S move. Then you set f of what? F of fp. So here I write fp, meaning that we have this base point equals b to the lambda. Here I have a lambda a b. No, a square b square. Sorry. And here I have a square b square to the minus 1. And if P and P prime differ by an A move, alpha goes to beta, then same thing without the square. So in genus 0, they can only differ by an A move. There are no S moves. Okay, so this is a recipe.
What is 2 alpha?
Tau alpha is the Dehn twist on alpha. So again, B is tau beta. So this is generated by Dehn twists. I want to give you a recipe which will compute the image on any Dehn twist. And I want to do it in a, quote, local Lego type way, which is this, which you can also phrase slightly differently if you want to make it even more Lego-like. But the recipe is this. You start from this maximal degeneracy, maximal multi-curve, and all you have on this is this.
What do you mean by F and this P? I don't think.
This is F sub P. Well,
Yes.
F sub P is the fact that you take P as your base point.
Oh.
So you pick a base point. So pick a base point.
And so your theorem saying that CPS is connected means that you're completely defined on every.
So so now it's still not quite working. So the theorem is. So I have to confess something. I mean, theorem is okay, but I made it slightly easier than it sounds. You have to complicate it a little bit. I'll say it in a minute. Theorem is if f is in dt hat, so which means f and lambda satisfies 1, 2, 3, okay? And f satisfies a relation, which I'll show, then this defines an action this is a well-defined action. So the missing relation is the relation which you've guessed it, which come from the cycle, the last cycle, and this is it. So you have to satisfy 4 relations. The first 3 we know already. So the first one is relation 1, the second one is relation 2, the third one is relation 3. And they come from, again, gamma 1, 1, gamma 0, 4, and gamma 0, 5. And the last one, which of course is incomprehensible because I didn't tell you who these loops were. They all live on gamma 1, 2. I must have a... Let's not go into this because, okay, I mean, we can do it later. They're just loops. They are the loops which you've seen on the screen when you had this cycle 6AS, and they have names, and this is it. So it's a relation with 6 terms, okay, and which involve exactly the loops. It says no. I mean, you can even say it differently. It simply says that if you go around that hexagon, which is not the usual hexagon, it's the hexagon of type 1, 2, then you return with 1. Okay, the pentagon, so if you go around the pentagon, you return with 1. Here you go around an hexagon, which is not the usual one, again, and you return with 1. So, so the theorem says that if this is satisfied, so if f is in GT plus 1 relation, then you're happy because using the other theorem, yeah, as you said, saying that this is connected and simply connected, you check that it does not depend. You have defined your action on any Dehn twist in a coherent way. So this is the same use as Maclane's coherence theorem. Now I've cheated a bit. Not much, because this is, as is slightly wrong. This is true, otherwise you have to put factors. This is true if you take lambda equals 1 and rho 2 equals 0. So lambda equals 1 is lambda equals 1, because when I cheated because I told you take a multi-curve, you should have told me. I mean, this is just purpose of exposition. I took a multi-curve as a base point. You're not allowed because you act on the base point around your point of maximal degeneracy unless lambda equals 1. You're allowed to take a base point. You're allowed. It's the same as here. You have 0. You have these two. If I'm not acting on this loop, then I can take happily all this as a base point, even if it's not simply connected, because I'm not acting on these things. So if lambda equals 1, I can take, that's easier. Slightly easier, not much easier, but slightly easier. Rho 2 equals 0, rho 2 is the Kummer character 2, and that's also very simple. It's because, I mean, I don't want to go into too much detail. When you map M11 to M04, you have a, what are you doing? You're doing this, x minus lambda. Okay? And you're mapping this elliptic curve to 0, 1, infinity lambda. But then suppose you go to infinity, I mean, well, no, or even 0. There's this 2. This 2, this 2. It says that if I have a tangential base point here, I map to a tangential base point, but the uniformizing parameter is not the same. And mark the fact that if a uniformizing parameter is not the same, it's not innocuous, because when I do this and I act with sigma, I get sigma of this will be 2 to the rho 2 of sigma, 1 plus rho 2 of sigma. Sorry, no, what am I saying? What do I want to say? Rho 2 of sigma t to the 1 over n. No, over n. The Kummer character is simply, I'm tired. The Kummer character is the thing which tells you how you act on the root of 2. Here, the root of 2. Okay? So if I don't act on the root of 2, then it doesn't. This and this are the same. If I do act on the root of 2, then there will be a slight twist. So this is completely correct. So I could erase this, and that's why it's not in the transparency. If you have these two conditions. So we wrote a paper with Leila like this, and then with Nakamura, she included in particular these two things, but you have to be slightly more careful. I mean, you have factors, but I prefer not to mention. So this gamma, so now you can restore this because again, it's relatively, it's not crucial. So this gamma is, so gamma equals GT sort of intersected with that relation. I don't know how to call it, coming from 6AS. And that thing, which contains the Galois group, where you can check. I mean, there is nothing to check really, because MGN is a stack. This is the 6AS. This is a miracle. 6A changing categories. 6AS is nothing but null homotopic path near the boundary of M12. And of course, the Galois group respects it by functoriality. There is nothing to check if you say it properly. So it's just true. The real thing is more that, in some sense, it's more that theorem, which tells you that this is simply connected. So this is coherent. I won't tell you about the two-level principle, which is a way of explaining these things again a little more deeply. But I don't think we have time, unless maybe during the questions. So let's stop here.
Thank you.
Shall we ask questions now? Pierre, shall we ask questions now? I think
Sorry?
short questions now?
Up to you.
Yeah.
You are the...
Things are fresh, or?
Yeah.
A really short question. You define the action after having fixed the tangential base points. How do we have control on how the action change?
This is what I mean. Defining the action is... I define the action by changing the base point. That's on the board. I say that if from one decomposition to another, what you get is a factor here. Okay? So, by the way, this factor commutes with everybody. Maybe that's another way of saying it's local. This factor commutes with everybody else in the two-pants decomposition. Everybody else is somewhere else. I mean, all the other loops are all the other loops are disjoint from alpha and beta. So this factor commutes with everything else. So you can put it in globally if you want. You see? So this is the way I defined it. So what it tells you is that the one and only ingredient, F, which controls, for instance, the way the Galois group acts on this straight line from 0 to 1, which you will see a lot when we will talk about multi-zeta, which Deline thought necessary to call le droit chemin, which is very judgmental overtones. So le droit chemin is the only thing you have to act on. And this is the same F for any G, any N, any whatever. So this is the only parameter apart from the cyclotomic character.
Any other questions? So what time do you want to start the discussions? 4?
Yeah, I mean, yes, if there is not room, but...
We have a room for this.
No, room for discussion means room in our heart and brains and whatever.